This is a diagram of the Large Hadron Collider. And there's all sorts of loops here. The point here is that they make these things go in a circle, and we do that by having a magnetic field, right? We've got a magnetic field that this thing is in, and that magnetic field causes these particles to go in a circle like that. And we can do that easily with a magnetic field, right? These are superconducting magnets that we use for this. And this is around, all the way around is like 27 kilometers. Here's a diagram of CERN, the loops and everything, what they are underground. So they're just ginormous. And so one question might be, why is this loop so big? And the answer is that the particles have so much energy that I think it's like 1,000,000 times more energy mass than proton mass, right? So when you look at the radius of the curve it goes around, it's mv over qb, right? And so the charge doesn't change as you accelerate it. The magnetic field, we max that out. That's like the limit of superconductors, right? Okay. And so as the mass gets bigger, and the mass is getting bigger and bigger because we're giving them energy. Energy literally has mass, E equals mc squared, right? So the change in mass is the energy that you've given it divided by c squared, right? So a particle, a proton flying down this tube has its rest mass, which is inconsequential. Okay, it turns out, I mean, protons are big particles as things go, but the energy that they've got, the kinetic energy divided by c squared, is so much bigger, right? The whole point of a particle accelerator is that you collide a proton with a proton, right? And journalists like to say, you throw a watch against the wall and look at the particles that come off, but that's not really it. What you're doing is it's like pitching two baseballs into each other. And briefly, when they collide, the kinetic energy of the baseballs creates an elephant, a short-lived elephant, right? And we never really directly observe the elephant. We just surmise its existence from the particles it decays into. And we do statistical analyses and lots of math. Okay, so basically these things have to be huge because when we get them up close to the speed of light, their mass just goes through the ceiling. Okay, the velocity at some point doesn't increase. It's essentially the speed of light. Right, it's just short of the speed of light, 0.9999999 times the speed of light, right? But anyway, this is super cool, right? This is a picture inside the tunnels at the Large Hadron Collider.